Hey guys, I hope you had a good break. I'm sorry, the other video that I made, which covers the first part of this, does not want to upload, so I've got to redo it. However, it's basic descriptive statistics, and since all of you had AP Stat, you should be pretty familiar with that. I'm going to post the mark scheme tonight to those questions that I put, that I gave to you, or that the substitute gave to you last block. And you know, if we need to, when I get back, and I hope it's very soon, I'll recover it in class. But I want to move into probability because I know some of you said you didn't really learn that much probability in AP Stat, and your test will be riddled with it. So it's really, really important. So I'm just going to do the first part because it's a lot of information. And these slides I had posted online last block, the PowerPoint slides that I made for this section. They're not all there, I didn't finish them, but anyway, I will finish them eventually in time for your exam and for you to know. So let's get started with this. Okay, in probability, just like in any branch of math, definitions are super important to know and understand. And again, I know this is kind of small. I printed 2 on a page for the recording, but anyway, you know, you've got the life size that you can rely back on EDSB. So you can look back at those if needed. But probability is just the likelihood that something will happen, okay? And a random experiment is just an experiment in which there's no way to determine the outcome beforehand. So, you know, I can't pull a dice out of my pocket and say, you know, I predict a 3 will appear. Well, I guess the 3 could appear, but the probability of it would be rather rare. It would be weird. So anyway, I can't predict the outcome of whatever experiment it is I'm trying to perform, so that would be called random. The trial is the total number of times the experiment is repeated. So if you toss a coin 50 times, then, you know, the total number of times you tossed it was 50. Okay, so, or, you know, tossing a die or something like that. And the outcome is a possible result of the trial. So maybe rolling a 2 or 4 on a die. And different results are possible for one trial of the experiment. Okay? An event is the set of possible outcomes of a random experiment. So, you know, for example, I have here the total of 2 die is 6. So, you know, the outcomes would be a 1 and a 5. So if I toss 2 die and, you know, I'm looking for a 6, the possibilities are a 1 and a 5, a 2 and a 4, a 3 and a 3, a 4 and a 2 and a 5 and a 1. Okay? And the random experiment, so I know I already said that earlier up here, but there is going to be uncertainty over which event is going to occur. So I may, you know, toss a coin 50 times thinking that I'll get more heads than tails, but I'm not sure. We got to see how many times that happens in the trial, the experiment. Now the sample space, that's really, really important. It's the set of all possible outcomes of your experiment. And the sample space is denoted with this, you know, it's usually this fancy U. You know, I can't write those, right? But anyway, N of U gives the number of elements in the sample space. So, you know, if you want to toss a die, then the sample space, you know, once you toss it, it could land on a 1, 2, 3, 4, 5, or 6. So the universe, or the sample set, sample space for this particular experiment is 6. Or you could toss a coin. Well, when you toss a coin, there are only 2 outcomes that are possible, heads or tails. So there are 2 elements in your sample space. If you roll a die and you toss a coin at the same time, well, you know, you could get 1 head, 2 heads. You get, I'm sorry, a 1 and a head, a 2 and a head, a 3 and a head, a 4 and a head, a 5 and a head, and a 6 and a head, right? Those are all the numbers that the dice could land on, and of course, you know, you could end up with heads or tails. So if you add all those up, the sample space for this particular experiment would be 12. Okay? The frequency of any outcome is just the number of times the outcome is observed. So if I'm tossing a coin 50 times and the outcome that I'm looking for is the number of heads that I see, then you know, I'm going to tally up every head that pops up, and I'm going to use that as my frequency. It's the number of times heads occurs in my experiment. Sorry, I'm having a little bit of coffee to keep me awake. And the relative frequency of an outcome is just the frequency of that outcome expressed as a fraction or percentage of the total number of trials. So the little formula here is at the bottom, the number of times the event happens over the total number of trials. Okay, so make sure you know those. They're really important to know, and that's going to help you with probability. Okay, so on the next slide, and you probably already know this, I mean, I think we learned this in grade school, but events that are certain to occur have a probability of 1, meaning 100% this is going to happen. And an event that cannot occur has a probability of 0. And probability will always be a number between 0 and 1 inclusive. Okay, so the probability that the total of 2 die is at least 1, well, if I toss 2 die, I have, you know, 36 possible outcomes. So if I get 36 over 36, that's a 1. I know I can toss at least a 1 when I roll 2 die. Okay. The total of 2 dice is exactly 1. Well, that can never happen because the lowest number on a die is 1. So even if I tossed a 1 and a 1, that's a 2. So that's 0 out of 36. And so that could never happen with dice rolling anyway. Okay. And we have different kinds of probability. And the first one is experimental, and that's where you actually conduct the experiment. Lucky for you, you're not going to have to flip a coin 200 times or toss a die 100 times or spin a spinner 50 times for your IB exams or any other exam. It's already going to be done for you. You're going to be given some information, and you're going to be working more in the theoretical aspect of the probability. Okay? But for fun, and these examples came out of the SL book because I like to start out small and work our way up into the HL stuff just in case you've forgotten or didn't know some things. But we have a small plastic cone that was tossed in the air 279 times. It fell on its side 183 times and on its base 96 times. A, what is the number of trials? Well, the number of trials is 279. That's the number of times we tossed the cone up to the air to see what the outcome was. Okay? What are the outcomes? Side or base, right? It can't land any other way. It can't land on the tip there unless, I don't know, it's weighted or something. So anyway, there's only 2 outcomes in this experiment, side or base. What are the frequencies of each outcome? Well, the frequencies are just the number of times that it landed on its side or the number of times it landed on its base. So 183 and 96 respectively. And what are the relative frequencies? Well, easy, right? The relative frequency, we want to say for the side, let's say, the cone that lands on its side. Oops. The cone landed on its side 183 times. There are 279 tosses. And so we divide those and we get 0.656, or about 66%. And the probability that this lands on its base, well, it landed on its base 96 times, and there were 279 total tosses, and so about 34%. So as the number of trials increases, the more confident we are that the estimated probability will be accurate. Sound familiar from calculus? As n approaches infinity, right? As the number of rectangles increases, as the interval width decreases, then we get more and more accurate with our outcome. So anyway, that's how you would do something very, very simple like this. So this is very, very simple, basic probability. And in IB, they're going to expect you to illustrate sample spaces in the following ways: lists, grids, tree diagrams, and Venn diagrams. Trees you'll see a lot. Venn diagrams you'll see quite often too. So you need to be very proficient with those, and you will be by the time I'm done with you. Okay? So here's another example. And again, I know it may be hard to see on the video. trying to get the camera a little bigger there. But again, these are all on the slide, so you can go back and find the corresponding slide. But this says here, list the sample space of possible outcomes for A, tossing a coin. Well, when you toss a coin, it's going to land on head or tails, right? You get two choices. So your sample space, you notice, has two elements, heads and tails. That's it. If you roll a normal die, well, again, there's 6 possible outcomes. It could be a 1, a 2, 3, 4, 5, or a 6. And so the sample space would consist of all of those elements, 1 through 6. Okay? You'll probably be asked that, believe it or not, at some point. Okay, the two-dimensional grid. You probably did this in science. What's that? Oh gosh, I remember crossing green beans with yellow beans. I forget the name of that little grid there. Blue eyes and green eyes when you do genetics. Anyhow, it's been a long time. You get the drift. You probably remember the name of it. But this is a similar idea. Okay, so when we have more than one operation, we can still list the possible outcomes. And sometimes we're going to use a grid. So not that you would necessarily have to draw one for IB, although it may come in helpful if you've got a particular problem where, you know, this would be beneficial. But sometimes IB actually gives you one and you have to interpret based on what you see. But anyway, here, you know, if we toss 2 coins, so we've got coin 1, heads or tails, and we've got coin 2, heads or tails. And, you know, what are the possible outcomes of tossing these 2 coins? Well, I could get a heads and a heads and a tail and a tail, right? And I missed one. Head, 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 tail, tail, head, tail, tail. So these are the 4 possible outcomes in the sample space using a grid. And another pretty good example of using a grid is this one here. It says use a two-dimensional grid to illustrate the sample space for tossing a coin and rolling a die simultaneously. From the grid, determine the probability of A, tossing a head. So, you know, you want to write, you see how they're writing here, the probability of a head, or you could do P of H, like I would write it, see if I can fit this in here. I would write it like this. That's okay too. Well, you know, if I'm tossing a coin and rolling a die, you notice down here we've got all the possible outcomes for the die. Up here they've got the possible outcomes for the coin. And so we want the probability of tossing a head. Well, there's 6 possibilities. I mean, we could, you know, get 6 heads. So 6 out of what? Out of 12, right? There's 6 here and 6 more here. So n is equal to 12 down here, so 6/12 or 1/2. Getting a tail and a 5, well, we want to see like where this grid sort of intersects. And here's the number 5, and here's all the possibilities for tails, and it intersects right here. So only 1 time out of 12 would we expect to get a tail and a 5 when we perform that experiment. And then finally, the probability of a tail or a 5. Well, here's all of the tails and here's the 5, and you notice that that's 7 out of 12. Okay, and the reason why is because that word or is very important. It means a tail or a 5 or both. Okay, so that word or is very, very important in math. Oops, sorry here. Very, very important in math, and so don't forget that it means a tail or a 5 or both. So with so we can get a tail, which there are 6 choices, or a 5, which is 1 choice, so 7 over the total number of outcomes, 12. Okay, then there are tables of outcomes, okay, and these you'll see quite a bit. And what's going to happen is you're going to compare 2 categorical variables, and usually they're going to result from a survey. So let's go straight to the example. So people are exiting a new ride at a theme park and were asked whether they liked or disliked the ride. The results are showed alongside the table. Now, I put this in here on purpose because IB will give you this table here. The table below is the same table, except it has total columns on the bottom and the side, and you're going to have to construct that. You're going to have to compute that for when you're actually doing a problem. Generally, IB will not give that information to you. So, you know, I mean, it's not like it's hard to do. We can add up the number of children, adults who like the ride and who dislike the ride, and we can total them up, you know, horizontally here. And then we can add up the number of children who both liked and disliked the ride, and adults who liked and disliked the ride, and add those up. And this number, 130, should sum these two, and these two should be the same. Okay? So, in A, you know, the question is, you know, what does this table tell us? Let me see if I can just fit it all in here. It says 83 out of 130 people, so that makes sense. 83, because this is children and adults, out of 130 people, that's N, total number of people who were surveyed, liked the ride. So the probability that people like the ride is just 83 over 130. Okay, then another thing we notice is that 17 children out of the 130 people surveyed disliked the ride. Okay, so the probability maybe that this was a child who disliked the ride is given here. Okay, was a child and disliked the disliked the ride. Well, that would just be 17 over 130. Then here in C it says 28 plus 30 plus 17 equals 75 of the 130 people are adults or dislike the ride. So here what we're looking for is the probability of adults or dislike the ride. So we're looking for adults, which is 58, right? Or dislike the ride. So are adults or dislike the ride or both? And so the 17 are the 17 children who dislike the ride. So anyway, when you add those numbers up, you get 75, so it's 75 over 130. Of the 72 children, 55 like the ride, true. So what's the probability that they like the ride given that he or she is a child? Ella, stop. So, probability that they like the ride, given that he or she is a child, well, that's the number of children over the total number of children. So, like the ride, given that he or she was a child. And of the 47 people who disliked the ride, so if you add those up, you get 47. 30 were adults. So, what's the probability that the person was an adult, given that he or she disliked the ride? Again, it's going to be 30. Adult, disliked, that's this number here, over the total number, 47. Okay, so you got to make sure you keep those totals straight and just pay attention to what you're reading. This was probably very easy for you, I'm hoping, so shouldn't really be an issue. You'll do some practice. Okay, compound events, those are just events with two or more favorable outcomes. And there's two different types of compound events. And when you want to determine the probability, each one is different. Okay, so let's look at independent events. Independent events, let me move this up a little bit more, like overkill now. Two events are said to be independent if the result of the second event is not affected by the result of the first event. So in other words, I toss a coin, I get a heads. I record that outcome, and then I pick up the coin off the ground and I toss it again. And, you know, I get whatever I get. Maybe it's another heads. So the fact that I get a heads the second time had no influence from the first toss. There's no connection at all. So the first event does not affect the result of the second event or the outcome of the second event. And replacement is key in independent events. So, you know, you have a bag of blue and green marbles, and you pull out a blue marble and you record its color and you place the marble back in the bag, and then you want the probability of, you know, choosing a green marble or something like that. So what's going to happen with independent events is that you're going to replace the thing that you're using. So a marble, a disc, you know, using the same coin, whatever. So Important definition. If A and B are independent events, then the probability of A and B, so and is another really big word in math, right? A and B equals the probability of A times the probability of B. And this rule can be extended out. I could have the probability of event A, B, C, D, E, F, G if I wanted to. It will just be P of A times P of B times P of C times da-da-da-da-da. Okay, so as long as the events are independent, I can just multiply the probabilities of each event and get the answer. Sorry, my dog's going a little bit nuts. Boris is teaching tonight, and I can't play with her or anything, and so she's like going insane, and so that's what you hear in the background, and I apologize now profusely. So here's a simple problem. A drawer contains 3 red paper clips, 4 green paper clips, and 5 blue paper clips. 1 paper clip is taken from the drawer and then replaced. Another paper clip is taken from the drawer. What is the probability that the first paper clip is red and the second paper clip is blue? Okay, well, you know, think about it. I have a total of 3 and 4 is 7, and 5 is 12. So I have a total of 12 paper clips. So what I know is my N is 12 here. And let's stop. And you know, they're all in the same container or bag or whatever. So if I pull out a paper clip and record its color and put it back, I still have 12 paper clips in the bag. So I have equally likely chances. So I wrote here, because the first paper clip is replaced, the sample space does not change. That's very important, because when you do probability without replacement, you got to be really, really careful, because your sample space will change when you don't replace something for the following events. So anyway, just keep that in mind. All right, so the idea is, you know, what is the probability that the first paper clip is red and the second is blue? So a good way to write that is the probability of red then blue, or probability of red then blue. You could write it like that if you wanted to, meaning red comes first then blue. Well, it's just the probability of red times the probability of blue. Well, we have 3 red paper clips, so the probability of the red is just 3 divided by the total number of paper clips, 12. So that's what you got right here, times the probability of blue. Well, we have 5 blue paper clips, so that would be 5 over the total number of paper clips, so 5/12. And when you multiply those together, you get something, after reducing, like 5/48. I like these kind of problems. I think they're a lot of fun. By the way, I'm learning very quickly that probability is tough to do on a video, so maybe it's just me, but I'd rather be at the board with some stuff doing it, but I think I'm doing okay. I mean, I want to like show you things, but anyway. Okay, so example, a coin and a die are tossed simultaneously. Determine the probability of getting a head and a 3 without using a grid. Okay, well, in my mind, you know, I've got the probability of getting a head and a 3. That's what I write down. And I know that, you know, by tossing a coin and throwing a die at the same time, well, first of all, they're simultaneously, but the outcome of this one is going to have no effect on the outcome of the die, or vice versa whatsoever. So I know that they're independent events, and so I know it's just the probability of the heads times the probability of a 3. And here you have it here. The probability that you get a head is 1 out of 2, right? The probability that you get a 3, well, if you toss a die, you get the numbers 1 through 6 respectively, so only a 3 can come up one time, so 1 out of 6, so the total is 1/12. Now there's dependent events, okay? And the result of one event is affected by the result of another, or the outcome of one event is affected by the outcome of another. And so when that happens, we say that the events are dependent. And if events A and B are dependent, then the probability of A then B is equal to the probability A times the probability of B, given that A has already occurred. Super duper important to know this. Okay, So you can write this, you might have remembered this somewhere down the line, B given A. So this little line here means given. This is called conditional probability, which we'll talk about next time. But anyway, you could say that this is the probability of event A occurring times the probability of B given that A has already occurred. Okay, so here's an example on dependent events. A box contains 4 red and 2 yellow tickets. 2 tickets are randomly selected from one box without replacement. So in other words, if I pull out a red ticket, I don't put it back. Okay, so you want to think without replacement for dependent events. Find the probability that both are red. Okay, so I want the probability of red, then red, right? Or red and red. So that's the probability of red times the probability of red. Now, we have 6 total tickets. N is equal to 6. We have 4 red and 2 yellow. So, in my little bag of 6 tickets, the probability of pulling out a red is 4 out of 6. That makes sense, right? But I'm not putting the ticket back in. So now I'm going to stick my hand back in the bag and pull out another one. Now there's only 5 tickets left in the bag, so you see my sample space has changed. Okay, and not only that, there's not 4 red tickets in there anymore because I pulled one out in this trial. So there's 3 possibilities left. So it's just 4/6 times 3/5, and you can clean that up to get 2/5. Okay, and then the second question is find the probability that the first is red and the second is yellow. Okay, well again we know that we're not putting it back if we choose a red one. We know our sample space is changing because once we pull a red one, let's say we have 5 left in the bag. So it's the probability that the first is red times the probability that the second is yellow given the first is red. Okay, and I write that like something like, I'll write it down here, the probability of a red times the probability of a yellow given the first one was red. That's a Y, not a 4. Okay, so that's what they did. If the probability of taking the first ticket is red, then that's 4 out of 6, same as before. And then my sample space has changed. Now I have 5 tickets left, and there's 3 red and 2 yellow in the bag. And so the probability that the second is yellow, given that the first is red, well, there's 2 yellow tickets for sure remaining in the bag, so that'd be 2 over the number of tickets left, so 2/5, so you get 4/15. Besides, this stuff's kind of boring to talk about. I'd much rather be doing calculus or something, I don't know, more application, I suppose. Tree diagrams. You're going to see these a lot, okay? And IB loves to use tree diagrams, and you're going to be using them when there's more than 2 operations involved. And you always want to draw your tree horizontally. So here's the example for the next one. So it always goes this way, okay, horizontally. And the idea is to draw one set of branches for each action in the experiment. So maybe raining and not raining or something like that. Or maybe, umbrella or no umbrella, whatever the scenario gives you. Label the events at the end of the branches and label the probabilities on the branches. So that's really, really important. If you don't worry about the example itself, but let me just zoom in on this a little bit. Can I? Sorry. I think this thing is like... There we go. Okay, so it's really important, especially on your IB exam, that you label. So you see this has to do with raining and not raining and biking and not biking. So they're letting this first part of the tree be rain or no rain, and they're listing the respective. So apparently there's a 20% chance that it's going to rain. If there's a 20% chance of rain, that means there's an 80% chance that it won't rain. So make sure you list those probabilities on the branches. Okay, and then what you're going to do is multiply out each branch to get the probability of each outcome, and the probabilities on each branch must always total to 1, because all probability adds up to 1, and the final probabilities must also total to 1. Okay, so again, it's on the slide. So let's look at this example, because this is a cute little example. I actually like it. I don't care for tree diagrams much, but they are helpful. I will say that. So, there's a 20% chance of rain tomorrow. If it's raining, there's a 15% chance I will ride my bike after school. If it is not raining, there's a 70% chance I will go biking. Find the probability that I ride my bike after school tomorrow. Okay, so again, I start out with how I read, okay? Raining, rain or not rain. So here are the two branches, rain or not rain, and their respective probabilities. Now if it's raining, I might ride my bike and I might not. And if it's not raining, I might ride my bike and I might not. You see that? So, you know, according to what they're giving us, if it is raining, 15% chance, 0.15, that I will ride the bike, which means that 1 minus 0.15 gives me an 85% chance that I won't ride my bike if it's raining. And if it's not raining, there's a 70% chance that I will ride my bike, and that gives us a 30% chance that I wouldn't ride my bike. Okay, so anyway, I said multiply each branch out. Well, the probability that I go biking tomorrow is given down here. So again, it's kind of hard to see. The probability I go biking tomorrow, well, is 0.03. How do we get 0.03? Well, if you multiply 0.2 times 0.15, I think that's right. Let me just make sure. Duh, yeah, it is. 0.03. Okay, so anyway, if I just multiply these branches out, the here that it rains and I don't bike, it's 0.2 times 0.85, so I get 0.17. Okay, and if there's no rain, it's 0.8 times 0.7, gives me 0.56% chance that I will bike if it's not raining. And if it's not raining and I don't take my bike, then if I multiply those out, I get a 24% chance that I will not bike when it rains. So they want to know, you know, what is the probability that I bike tomorrow? Well, I bike here and I bike here. So if I just add those two probabilities up, looks like there's a 59% chance that I will ride my bike, rain or shine. Okay? And there's some little notes down here. Again, the probabilities for, you know, the labels are marked on the branches. IB is going to want to see that. There are 4 alternative branches, each showing a particular outcome. All the outcomes are represented, and the probability of each outcome obtained by multiplying along its branches. Now, if you add these probabilities up, they should equal to 1. Okay? That's what the probability has to do. Okay, I think I'm getting a little tired, and so I'm going to stop maybe at this slide. Maybe I'll go on. But we have sampling without replacement. So this occurs a lot in industry, especially, you know, when they're making widgets or something. So I don't know, maybe Apple's making the new iPhone and they want to test how many defective phones are in a batch of, I don't know, 1,000 or something like that. So a lot of industries who produce widgets or things that we like to buy, they'll often test their products to make sure there are no defects. Calculator makers, keyboards, you know, you name it. Okay, so what they do is they choose an object at random from a large group to inspect. So if you think of a conveyor belt full of, I don't know, what's this thing on the cell phone? PopCap thing? These things, right? Mine's filthy. But anyway, you know, mine doesn't work that great anymore. It used to, but anyhow. Got some weird thing about the president on my phone just now, but anyway, you know, you think of all these pop caps on a conveyor belt, thousands of them, and some guy walks around and takes one here and takes one, you know, 3 miles down the conveyor belt or something, and then they test them and all that, okay, to see what's going on with it. Okay, so if the object is put back onto the conveyor belt, then that would be sampling with replacement. And if it's not put back, it's called sampling without replacement. So I pull a pop cap and I inspect it for something and I put it back on the conveyor belt. That would be with replacement. Okay, sets and Venn diagrams. So this is yet another way we can represent data and things. Okay, so when we roll an ordinary die, the sample space, or the universal set, which we call U, is 1, 2, 3, 4, 5, or 6. Those are the possible elements in our set. If the event A is the number less than 3, then there are 2 outcomes which satisfy the event. We can write that A is equal to 1 or 2. There are only 2 numbers on a die that are less than 3. Okay, now we can represent this with a Venn diagram. So you always make the universe, which is the rectangle, which is U, and you put a circle, or 2 or 3, depending on the situation, in your Venn diagram, and they're calling the elements inside this circle event A. So if event A is the number less than 3, then the only 2 elements that can go in this subset of the universe is 1 and 2, right? And all the rest of the numbers on the die, or the possible outcomes, end out inside the universe. So we would say that, n of U is equal to 6, and n of A is equal to 2. So the probability that event A occurs is n of A over n of U, meaning the universe, or 2 out of 6, which is 1/3. Again, I know that's really tiny, but it's on the slides. I think I'm going to go this one more slide and then I'll stop. Okay, so again, this whole rectangle is our universe, and we can have many sets and subsets inside. One very important thing is called the complement. I have elements in A, but I have stuff outside of that subset A, so we call that A prime represents the complement. And what I know is that the elements outside of the circle, or the subset, plus the elements inside the circle all have to add up to 1, the probabilities of those events. So what I know is that P of A plus P of not A must equal to 1. The total probability has to equal 1. Okay? So if our universe is the numbers 1, 2, 3, 4, 5, 6, 7, and A is the event 2, 4, or 6, then the complements all the numbers that are not 2, 4, and 6, which is 1, 3, 5, and 7. So event A is that an even number will appear, and event not A, or not in A, are the odd numbers. Okay? You already know these. X is an element of set A, and n of A is the number of elements in set A. Okay? Now we've got the intersection, and again, I know you know intersections of sets. Okay, so again, intersection is A intersect B. All right, so this set contains all elements common to both sets. So we're talking about this little region right here. We have set A, we have set B, and where they overlap, that's the intersection. Okay, so the intersection of two sets is the set of all x such that x is in A and x is in B. So it's in both sets. Okay, and of course the union, that's all of this shaded region. So AUB, the union of two sets, in this case, it could be 3 or 4 sets, it depends. It's the set of all x such that x is in A or B or in the intersection, or both. So that word or, so intersection goes with and, so I wrote that up there, and union goes with the word or. Okay, so it's in one, the other, or both. One more. Disjoint sets. That means they don't have any elements in common. So I have a set A, I have a set B, and the intersection's the null set. Okay, so this thing here represents the null set, not 0. Okay, it's completely different. So when you're writing a 0, write your 0 as 0. And the null set, meaning it contains nothing, it's empty, or the empty set has the 0 with the slash through it. Okay? So we would say that they're mutually exclusive. And it just means that the events cannot happen at the same time. They can't happen because they're disjoint. Now, the next slide is a very busy slide, and I would encourage you, because it's an example with the answers, to look at this. And I'm going to stop here. I'll make a note to self to stop. So suppose A is the set of all factors of 24 and B is the set of all factors of 28. The universe is the set of all x such that x is between 1 and 28 inclusive and x is an integer. Find the intersection. Well, okay, I would write out the elements of set A. Okay, it's all the factors of 24. So here they are. And set B is all the factors of 28, and here they are. And I know that the intersection means that the set that's common to both, the set that's common to both events. Well, you know, if I fill in my Venn diagram and I make A and B, then what's going to overlap is the 1, 2, 4. And, you know, I really don't even need to do that because I can see 1, 2, 4 is in set A and 1, 2, 4 is in set B. So numerically, it just makes sense. The other thing is I could look at the union. So that's A or B or both. And that's going to be the set of factors of 24 or 28 or both. And so they're listed right here. Okay. B was to illustrate on a Venn diagram, and IB actually makes you, they require you to do that quite a bit. So anyway, we'll do more with Venn diagrams next class. I'm going to post some IBQs for you on simple probability for you to play around with. And remember, if you have questions from the last video, please let me know. I'm going to post the mark scheme, but if you need help, please let me know because I can at least lay in bed and look over these things and then, you know, do a follow-up video with an example or answer you through a remind or whatever, okay? So don't hesitate to let me know. You guys have privilege to the cell phone more than the rest of the kids. So let me know. I hope this helps, and I'll see you next time. Good night.